My name is Juergen. I'm from Criteo here, data analyst. So my topic is outlier detection at scale. We're trying to track metrics for ad campaigns and raise outliers when there's a problem, right? So before I start, I want to say that a little bit about how this project came about. Some of you might know the project Science to Data Science, and we've had a couple of brilliant PhD people coming here for 4 weeks. They have taken on a first start that we had on this project and developed it much further. And so much of what I'm saying here has actually come out of this process, and some of them are actually here today. So credit where credit is due. All right, so quick overview. First, I'm going to say a few words about what is Criteo, what do we do, because that's important for the alerting system later on. Just the metrics that we talk about, etc., to have a context. Then why do we want an alerting system? What's the case for it? And then the main bit is going to be structure of the alerting system. So what are the components? How do they work? How do we implement them? Right. And finally, I say a few words about once we have the alerts, how do we push them out to relevant people? How do we visualize them? Right. Okay. So here, Criteo. So what we do is essentially the following. We have a lot of advertiser clients. They have their websites. That could be retail, travel, classifieds, all sorts of clients. So you as an internet user, you go on there, you want to buy something, or you want to look at products. Because we work with the advertiser, we then register that via cookies. So we don't know you as a person, but we know you as an ID and what you do on that website, right? So you look at products, etc., etc. And after a while, you go on serving the web in a wider scope. So you leave the advertiser website and you go on to other websites. And those websites hopefully then are publishers for Criteo. So publishers in the sense that on those websites we can show ads, right? So that's number 4. Yeah. So you go onto a publisher website. Because you have the same cookie, we can identify you there. And based on data that we have collected, so the products you've looked at, etc., we are then going to show you a banner, in this case about shoes. And then hopefully the idea is that you will click, which means you go back to the advertiser website and you might even purchase, right? So that's essentially the business we're in. Okay. So So on the left with advertisers, we have Criteo in the middle, and then we have publishers on the other side. Criteo is connecting these two pieces. Now, this whole system is a very complex system for various reasons. So, for example, on the advertiser side, with each of the advertisers, we have integrations, which means we have implemented code on a website. There are lots of parameters for that integration, etc. So that's already one source of complexity. Similarly, for the publishers, we integrated with all those publishers, and there are lots of different publisher technologies. Each technology is different, each technology has its challenges, etc. Another source of complexity. But the main piece of complexity is Criteo itself in the middle, for several reasons. So this process of showing banners to users, we make it valuable for both the advertisers and the publishers. And we make it valuable by using a prediction engine, so various engines actually. So we have to predict what will the user like in the banner, what makes him click, what makes him convert, right? So those engines are a major source of complexity. They're essentially a collection of machine learning algorithms. And as you know, some machine learning algorithms are by design black boxes. So you don't understand exactly what happens when you fiddle with one input to the output. But even if a specific algorithm is not a black box, because this is a complex engine, you have a collection of algorithms, and they all work together, so that in the end, even though it's not black, maybe it's at least gray, right? Then you put in the component from the left and the right, and together we have a very complex system. So obviously that system can go astray. and we want to avoid that. Two main reasons. We want to create reliability for clients. That means advertiser clients and publisher clients, so that if something doesn't behave normally, we want to be reacting immediately almost, going back to the root cause and fix it, right? But obviously there's the other benefit that sometimes, not always, but sometimes we might lose is a financial loss on the part of Criteo. It can be a financial loss on the part of publishers and advertisers, of course, but also we want to minimize any loss that we could make, right? Okay, so the alerting system is supposed to bring those two benefits. So what are the main requirements that we have on the alerting system? One main requirement is it should be scalable, and the reason is on the right here. So these are approximate numbers; they grow all the time. But I think we're actually in 130 countries now. So on the advertiser side, we have 12,000 of them, ish. Which each one of them we have integrations, etc. Then those advertisers have campaigns, so we're running of the order of 20,000 campaigns, and then each of those campaigns is active on many publishers, of which we have 17,000. And then this happens on desktop, mobile, tablet, and then of course for all of this we want to track not just one metric, because there is no single metric that would give us if something goes wrong, that metric would do a blip. So we have to track several metrics. At the moment, we're around about 10, but this should increase, hopefully, in future. So overall, per day, we do about 2 billion displays, which is essentially the basis, so the database that we draw from every day for this alerting system, right? So another requirement is should be flexible. So we have a hierarchy here, or hierarchy of analysis here, and that's going to come up later again and again. So we could look at the whole country. Say we want to look at the KPIs, at the metrics, or for the whole UK, right? So we want to see if something goes wrong with the country. We could look at it in the client level. We can go further down at the campaign level and device, and all these levels will behave very differently, right? So that flexibility needs to be built into the alerting system. The first factors up here, they're time invariant, right? So you could maybe think about implementing them manually. But what's certainly not under control is the bottom point, which is depends on time. So some advertiser might decide to double the budget, so we can deliver completely different performance, which is going to be at different time series. Competition on the market might change during sales days, etc., etc. We have seasonality in travel. Everyone wants to buy in January, and it's different from later in the year. So this flexibility is essential if it's to be running at scale, right? And finally, it has to be robust. We want to minimize false positives, because the usefulness is very much tied to that. If we have 20,000 campaigns with 10 metrics each and we raise 10% or even more false positives, it's very quickly going to be unusable, right? Okay, so we're going to see how we implement all of these points. So just a few examples. Here we have this place that we have as a time series. So this is actual data. And we have them in here every hour, right? And so you see the daily variation. At night it goes down, during the day it goes up, and then suddenly at the end we have twice as many displays than we had all the days before. So here we ideally want to immediately say, go and look, there's something probably wrong here. Another case which is maybe a bit more tricky is this one here, where normally at night things go down, displays go down, but in this case it then just stopped, goes down to 0 right away. So this is a bit tricky, because you would go, okay, the trend is this, but then we stay down here for a whole day. There's another case. Okay, so let's move on to the alerting itself, so the system itself. So this is the structure that we have of it. We start with data preparation. So we pull in the data from a database, and then you need to fill in missing values. You need to prepare the data for the actual computation. And yeah, that's actually a very interesting step that we'll get onto, the data structure that we use there. Then we put it into the time series decomposition. So we want to take away everything that's normal, and we want to leave to be left over only with a remainder that has the interesting bit in it. Then we put it into anomaly detection. So we take the remainder and we look at, is it just noise, or is there actually something that we should flag? And then finally, once we have the alerts, we want to say, what is the bottom line impact right at the point of detecting the alert? And then also what's in the last point is we want to push it out, visualize it, push it out to the people in charge of the client or the campaign that we look at. Right. So I'm going to now, okay, so the 2 points here. The design of this is absolutely fully modular with defined interfaces, so that if we fiddle with this, as long as we keep the interface constant, the whole system keeps working. And for all of these components, it's the same story. That reduces maintenance and facilitates if we want to improve it in future. So there's probably no one best way of decomposing time series. So you can think of this as good practice. Yeah, so how do we actually now build this system? And building this from scratch, as you probably know, is a very difficult task. But luckily, there's something called R that helps us stand on the shoulders of giants, and we can use all these packages. One thing that I think is really great about R is the whole R ecosystem. So the tons and tons of packages that people put in, the community that drives it, and that you can rely on. Right. And this is what we have done here as well. So data preparation. So this is about loading the data and getting it ready into a data structure that we can use for the analysis. So what we did here is we have a tree in the mathematical sense of the word, where we have the metrics that we want to track. So maybe I'll say a few words about the metrics themselves. So we have displays. So these are the banners that we show to people, the number of them, clicks, how many click on them. Then the click-through rate is just the rate at which displays get turned into clicks, right? And then what we do is we charge our advertisers on a click basis. So each time there's a click, we charge the advertiser. And that generates revenue for Criteo. On the other hand, we pay publishers each time we show a banner, and that's showing a banner as an impression. So we have a cost per showing an impression, and that's a cost that's generated for Criteo, and then that turns into a profit. So this is a mathematical tree that is represented in R using the package data.tree. And I think it's a fairly new package which could be useful because it has a very general tree formalism that can be applied in many different circumstances. Right. So one great thing about this data.tree package is that you can define custom fields. So each element in the tree, we can give it properties. And in this case, we give it arithmetic relations. So the tree knows that profit is revenue minus cost. And that allows us that, say, if we have the data at a campaign level, so for each campaign, we have cost and revenue, but we want to analyze it at a country level, then we can use the information stored in the tree to sum those quantities and recalculate at the higher hierarchy level of a country, right? Without manual intervention. Maybe just one comment here. This field is yellow because the cost per click is something that is changed by hand, so either by the client, by the advertiser, or by Criteo. And so this is a very special time series in that sense. So on the data.tree topic, it is a very simple code to actually implement the tree. So say we want to implement what's on the left there, on the right. The package has an object called node, which has methods. So you just run the new method on it, and you give it the name of the node or the element you want to create. And in this case, profit is the root element, right? And then you give it just the properties that you want it to have. So in this case, it has a difference property, which is the arithmetic relation there. And we also say it's summable, which means that if we want to go to a higher level in the hierarchy, we can just sum all of those numbers, right? And then we set up the root node. And then we want to set up its children. We just add a child to the profit node called revenue, which is a new element in the tree and a similar cost child. And then automatically, because of this operation element, we have this the ability to calculate on that tree, right? The other thing that's very nice is because it's a tree, if we decide to add additional metrics, which we sure want to do, then you just expand the tree and add the corresponding connections and the corresponding relations, right? Okay, so now we have loaded the data and we have it in a form that is useful for the analysis. So we pass it on to the next module, which is the decomposition of the time series. Yeah, so here we want to extract everything that's normal from everything that could potentially be abnormal. And one well-known way of doing this is the STL decomposition. So up here we have the data. So I think this is actually what I showed, one of the examples I showed earlier. So you feed it into the STL, it finds out what's the seasonal component, so here the daily variations and what's the trend. And here the trend contains a weekly variation as well. So weekends typically behave different from during the week. And when you subtract these two elements from the original data, then you have a remainder left over, which typically should be noise. But then we see already at the end there's a nice bump that we can then use in the next step. So STL uses a lowest fit, which is a local fit to the time series, which is coming back to that point about flexibility. So say we have a client here that changes its budget, in this case budget reduction, and then we have to accordingly adjust volumes. The time series decomposition, because of its locality, it adapts to that new behavior and it then automatically carries on, right? So on the right there you see the command. It's in principle it's very simple. You just have STL, seasonal trend lows, you put in a time series and then the seasonality window size, which here, this is the minimum according to the research paper that produced this. There's a bunch of other parameters. You can put in a window size for the trend, you can define a degree of the polynomials that are fitted in Lois, etc. And these are parameters that can be used to optimize the whole process. I think STL is part of the stats base part of R. And now we have decomposed the time series, we have a remainder, and that gets pushed on into the next module, which is the anomaly detection. Now obviously we want to find the abnormal behavior. And so one main method that we have used here is the two-key method. So you feed in the remainder, which is the black line here, over time. And it very nicely looks, I mean there's some sort of regularity, but overall you could say it's noise. Then you construct the two-key fences. So you use, in this case we use a rolling window of past data. So you sit at a data point and you look at the window before that data point to construct these green lines, which are the two-key fences, and then whenever the data shoots outside of that, we have the potential for an alert, right? So one thing to note here is because I should have said probably. So what we wanted to do is to do this every hour on the whole, on all campaigns and all clients, all countries. So every hour we get in a batch of new data, and then we want to raise alerts only for that new point in time. So we're not going to say, okay, based on the new data, yesterday we had an alert. Because then the whole point of the alerting system is defeated. And also we're using a rolling window of data that goes into the past. So that's contradictory to what we want to do, right? So the way we construct the way the Tukey method works is that with this rolling window, we collect the data from the past, we compute into quartile range, and then that gets multiplied by like a stretch factor that is sort of the sensitivity. If we increase the factor, we get higher Tukey fences, and it will take longer, a stronger outlier to raise an alert. If we multiply with a smaller number, of course, it'll be more sensitive. So these are parameters that we have in the system, and one main piece of work is then to calibrate it, right? So you want to set these parameters to values that, as I said earlier, they detect all the alerts that have to be detected, but then the percentage of alerts that get detected beyond that has to be minimized. And if it's not possible to minimize that to a level that the relevant humans afterwards can deal with, then the system would be useless. Right. Okay, then finally, so now we have the alerts and we ship them on into the final step. We have things like estimating the bottom line impact based on the data that's up to that point available, which is probably not the final impact it'll have, but nevertheless. Then you can filter alerts. You can say, all right, if the impact is below a certain threshold, we're not going to bother with it. If there's too many, we're going to filter them out. And then, of course, the main bit is we have to visualize them and send them out to the people in charge, right? So, and that's, as a data scientist, sometimes you skip a little bit over that because the job is done. But in this case, this is essential because the people then need to go into the data, find out this is the root cause, we need to fix it. So we have to make it as easy as possible for the people working on those alerts to do this. And that means, for example, if an account manager, so they will be the people that receive the alerts, if they have several clients and multiple campaigns, if there are alerts on several of them, then they should be bundled together. So they shouldn't receive alerts separately, and here and there it should be bundled together in a nice format. It should include all the information that we need. So was the analysis at a client level? Was it a single campaign? We need to do relevant KPIs. So of course, what's the KPI that the alert was triggered on, but also all the KPIs that are connected to this one, so that we can sort of start going into the right direction for analyzing the root cause. And then we need to find the visualization of the alert, of course. So then the other point is that we haven't really done yet, but I'd like to do is to have a feedback method, so that if we have false positives, that the account manager actually can come back and say, there shouldn't be one, maybe even for this and that reason, and then the parameters get adjusted so that this doesn't happen again. It's a sort of a bit of a learning alert raising system, right? So at the moment we have two ways of doing this. So raising, communicating the alerts. Our amazing PhD students, they also built a Shiny dashboard for this. And we have a different system already in place also, which sends out emails with all the alerts bundled together. So we'll have to see which one we eventually go for. But I quite like Shiny. And so here's, yeah, I don't have a demo of the Shiny page because I broke it recently. Otherwise, so unfortunately it's only a screenshot, but yeah, what we have is, we have, so you have, up here you have the client. It's probably a bit small, but up here in the blue section you have the client. You pick the client, it's given by an ID here. Then underneath you have the KPI. So there is a, there's a KPI selection here, so you want to displays or clicks or revenue, spend. You select the KPI that you want to look at, and then you have this very nice visualization here where you have a slider that gives you you can pick the subset of the time, of the whole time period that's available. And you have a zoom capability into this as well. And then down here we have the alerts. And so those alerts then are also flagged in this KPI plot, right? And then there's actually, so this is sort of displaying KPIs for the advertiser side. But we also have a similar page where we go to the publisher side. So if anything is wrong on a specific publisher, you would have a similar breakdown, right? Okay. So now, what are some future directions that we want to go in? So I have mentioned lots of hierarchies, lots of levels. We have country, client, campaign, but we could also, or we want to go into publishers, of which another 17,000. Then we have different devices. So if things go wrong on mobile, it doesn't have to go wrong on desktop, for example. Then we want to increase the number of metrics that we track. So here's average order value. So this is the average basket value that people buy on for the advertiser, the margin that we're making, etc. So this is one interesting part to extend. And then, so I didn't mention, but for the anomaly detection bit, we don't have just one anomaly detection method, but there is a couple of them, and at the moment they're chained. So it's actually two at the moment, but you can chain more of them, and the alerts just get aggregated. So if an event is an alert, if at least one of the detection methods detects them. But there is obvious ways of doing a better job there. So in sort of this, in the sort of data or statistical learning way of ensemble, you can have several detection methods and not just aggregate everything, but have a majority vote or other sort of ensemble type learning system, which could make it more reliable and reduce false positives. And then the other thing is, if we scale this to more levels of hierarchy, more metrics, etc., then we might get a problem with running it every hour at full scale. And so one option that we could do there is we pull the data up to a certain point in time, and then overnight we do a forecast. So at the moment we just take the data and then analyze it. There's no forecasting in the time series involved. But we could overnight make a forecast for the next day and then only pull the new data and make the comparison, which is a much simpler process than analyzing it in the full pipeline every hour. And I mentioned the feedback system for users that we'd like to do. All right, thank you very much.